Okay, here we go on the Chapter 1 review, Limits and Continuity worksheet. We'll start with number 1. And number 1 is the limit as x approaches 1 of x cubed minus 1 over x minus 1. And you're supposed to solve this one by filling in the table. So first thing, I don't know how much you'll be able to see on the calculator, but I'll talk you through it. Let's talk about how to put this function into our calculator. You're going to hit y equals, and then if you have anything in the top slot, you're going to hit clear. Occasionally you have to hit clear twice. Now to enter this function, we're going to start with parentheses. You're going to do parentheses x, and then use this caret, we call it, 3 for the cubed. Now if your calculator has the new kind of math print, you have to hit the right arrow button to get out of the exponent, and then minus 1, close parentheses, and then you're divided, and then start your parentheses again and type x minus 1. And then when you're done with that, since they want us to look at a table, they want us to make a table on this worksheet, let's hit second table. And here we have a table. And we're going to actually type the x values in. They wanted us to do 0.9, 0.99, 0.999. We know we're going to get an error for 1, but we'll put that in anyway. 1.001, 1.01, and then 1.1. And then what you see is the calculator gives you all the values. And I get, for 0.9, I get 2.71. For 0.99, I get 2.9701. For 0.999, I get 2.997. So you already can see that it looks as if this limit is going to be 3, right? Because those numbers are getting very close to 3. If we look the other way, if we start at the right end of the table, 1.1 gives us 3.31. 1.01 gives us 3.0301. So we are getting closer to 3. 1.001 gives us 3.003. So definitely as we look at this limit for both sides and we fill in that table, we can see that as the values get closer to 1 from the left, it's going towards 3. And as the values get closer to 1 as we go towards the right, the function is also approaching 3. Therefore our limit would have to be 3. Okay, one thing, if your calculator would not let you put in these x values, then what you do is you go to the table set. It's right above the window button. So you hit second table set, and you make sure your independent variable is set to the word ask. So independent is on ask, dependent is on auto. When you do that, and then you go to your table, it allows you to type in x values. Okay, let's look at number 2. Now, number 2 through 7, I guess, use a lot of graphs that are on your worksheet, and I reproduced them here kind of just with Sharpie, and I'll talk you through number 2 through 7. So number 2 asks, for which graphs is f of 2 defined? And that means the way that's written, it's asking for the function value. So let's look at each graph and see, is there a function value for 2? In letter A, here's x equals 2. Is there a y value that corresponds? Is f of 2 defined? Yes, right here where this black dot is. I think that may be at like 2.5 on your worksheet. So there is a defined value for A. For B, we have an open circle on your worksheet. An open circle means that the function is not defined there. So just by definition, letter B does not have a function value for f of 2. It's undefined. Letter C, we've got a vertical asymptote here. There is no function value for f of 2. Remember, f of 2 means x equals 2. Is there a value for y? So let's look at letter D, f of 2. If we look at letter D, we can see this black dot. That is the defined function value. And I believe if you look at your graph, you see that when x is 2, y is 1. And then look at letter E. When you look here, I think again when x is 2, y is somewhere between 1 and 2. So f of x is defined for 2 there also. Okay, so I think the only two that did not have f of 2 defined were B, because there's an open circle, and C, because there's an asymptote. Okay, number 3. For which graphs does the limit as x approaches 2 of f of x exist? Now remember, for a limit to exist, the right-hand limit and the left-hand limit must agree. So let's see. Let's look at letter A. If we are driving down this graph from the left, will we end up in the same place as if we were driving down the graph from the right? We will. We'll end up in this open circle. So yes, the limit exists. Letter B. If we're driving down the graph from the left and driving down the graph from the right, at x equals 2, will we end up in the same place? We will. I mean, the bridge is washed out. Remember, that's what I said the open circle was. The bridge is washed out, but we're both in the same place. And as we look at letter C, what happens here is both sides go to infinity. There is no limit here. And even though it looks like they're both infinity, so you might think that they agree, they don't, because we could never reach the same place. Okay? Well, because of that asymptote at 2. So C does not have a limit for x equals 2. Letter D. If we're driving from the left and we're driving from the right, we definitely do not end up in the same place. The limits from the left and right do not agree. Therefore, the limit as x approaches 2 of f of x does not exist. And let's look at E. As we drive from the left and the right, oh, no problem. That limit definitely exists. Okay, number 4. Which graph or graphs are continuous at x equals 2? Remember, the informal definition of continuity is that you could do it without lifting your pencil, right? We're looking for a graph that isn't broken and does not have a hole in it at x equals 2. Well, there's a hole in it here. And the technical reason why this one is not continuous at 2 is that the limit and the function value do not agree. So let's look at B. Well, there's obviously a hole in the graph, so that is not continuous at 2. And if we're thinking of the technical reason, it's because f of 2 does not exist. Therefore, it cannot be continuous at x equals 2. And letter C, definitely not continuous at x equals 2. And the reason can be either that the limit doesn't exist at x equals 2, or it can also be that the function value doesn't exist at x equals 2. Letter D, not continuous. We have to pick up our pencil. So the graphs don't agree here. We have a broken graph. And how we say that in mathematical terms is the function value, f of 2. Oh, I'm sorry, we say there's not a limit. Yeah, the limit doesn't exist, so therefore it's not continuous at 2. And then on letter E, this is a continuous graph. There are no holes, no breaks in it, so no problem. This one is continuous. Okay, number 5. Which graph is continuous for all real numbers? So we're looking for a graph that has absolutely no holes and no breaks in it. Our only option is letter E. Now don't let these dotted lines throw you. When we say for all real numbers, we mean all the possible x's. So no matter what x I put in, I'm always going to get a y value here. So we're fine. As long as you can put in any x and get a y, the function is continuous in this case. Okay, which graph has vertical asymptotes? This one would be the only one. This is vertical. There's obviously an asymptote here. The dotted line helps us discover that. And how do you write the equation of an asymptote? Well, it's written very simply, x equals 2. And number 7, which graph has horizontal asymptotes? Actually, a number of them do. So letter B, I think the dotted line is visible on your paper, and that would look like as x approaches negative infinity, the graph is trying and trying to get to 1. The other one that I think has a vertical asymptote is, a horizontal asymptote, is letter E. I'm not sure if the dotted line shows up on your Xerox. As x approaches positive infinity, the graph is trying to get to 3. As x approaches negative infinity, the graph is trying to get to -1. Okay, that completes the first page of the Chapter 1 review, and I'll stop the video and restart for the second page.